In an earlier video, we had touched on equilibrium, and at the time said that that was when the acceleration was equal to zero. And I had also mentioned at that point that we are going to have to add in that the angular acceleration is zero. Now, at the moment, I'm just taking a look at equilibrium where all the forces in question are confined to a plane. And this sort of case happens more than you might think, and so that's all right. Now, when we looked at it before, we had kind of swept the angular acceleration being zero under the rug a bit and said we'll worry about it later. Well, later is now. So this does mean that to a physicist, if you imagine, say, playing air hockey or something like that, after the puck has left the striker, as it's sliding along the bed of air, the forces are basically zero. And you may very well have the air hockey puck be spinning about its axis while it's doing that. That's part of how you can get the puck to bounce off the wall in a way that's unpredictable to your opponent or something like that, right? But believe it or not, to a physicist, this object that's moving at a constant speed and rotating at a constant rate, that's an equilibrium. You would think that you could define equilibrium a little more strictly, because after all, we usually think of equilibrium as just things being still. I called static equilibrium before, and I had to include the idea of saying, well, a skier going down a hill at constant velocity is dynamic equilibrium. But it turns out, no, this is really the strictest you can define equilibrium and have it make sense, oddly enough. So at the moment, since all of our forces are confined to a plane, all of our torques will be trying to twist something clockwise or counterclockwise. So what this gives us, in addition to the acceleration being zero before, and again, we're just considering forces in a plane, so we only need x and y, is we now require that the sum of the forces in the x direction be zero, the sum of the forces in the y direction be zero, and the sum of the torques be zero. So this means that we can solve for potentially up to 3 unknowns. So we'll just start with a very straightforward example. Let's just think about a teeter-totter. So if you've ever played the game of played with a teeter-totter, you know that usually you have a kid sitting on either side of the teeter-totter. And here I'm going to draw one of the kids to be a bit heavier than the other kid. In fact, we'll go ahead and say this kid has a mass of 50 kilograms, and this kid has a mass of 25 kilograms. And just to make the problem more straightforward, we'll go ahead and say that the plank on the teeter-totter is massless. So if you've ever played teeter-totter under these kind of situations, you know that usually the bigger kid is going to win and the little kid is going to go flying. That's why when you look at a lot of teeter-totters, you'll see that you've actually got the ability to change where exactly the fulcrum pushes on the teeter-totter. And this is so, say, the teacher during recess or whatever can make the game a little more fair and at least make sure that the little kid isn't going to go into orbit. So we'll go ahead and think about this example here. So let's say that, just to make the numbers nice and easy, let's say the length of our teeter-totter is 3 meters. And what we want to know is how far from the heavy kid, call it distance L1, should the teeter-totter be in order to make the game fair. And by make the game fair, that's going to mean require that the forces be 0. So this means that we'll actually be in static equilibrium here. While we're at it, we'll also go ahead and solve for the normal force from the fulcrum. Now I'm just going to go ahead and dimension another lever arm here. And we'll say that the distance from the skinny kid to the fulcrum of the teeter-totter is L2, which is the length of the entire plank, minus the distance from the fulcrum to the heavy kid. Okay. So with that, let's go ahead and draw an extended free body diagram where we'll just make the system the plank, the teeter-totter plank, and the two kids. And there's the one kid. There's the other kid. All right. So if the system is, so this is our extended free body diagram. So our forces are going to be the force of gravity, and we'll say that that is acting there at the heavy kid. We'll have a second force of gravity, half as long, acting on the light kid. And then we'll have a normal force pushing up from the fulcrum of the teeter-totter. Otherwise, the teeter-totter board would just go flying right through the fulcrum and crash into the earth. So let's go ahead and write down our equilibrium equations here. First off, sum of forces in the x direction is 0. Well, that's automatically satisfied because there are no x components of any forces. Great. So now let's go and write down the sum of the forces in the y direction. Sum of forces in the y direction should also be 0. We'll have the normal force up minus Fg1 minus Fg2 equals 0. So the normal force equals Fg1 plus Fg2. The force of gravity is mg, so m1g plus m2g. We can pull out a g, m1 plus m2g. And we get that that's 50 kilograms plus 25 kilograms times 9.8 newtons per kilogram is 735 newtons. Yay. Now notice so far, although I did suggest some lever arms here in this dimensioning, I haven't yet picked an axis of rotation to analyze this system about. And it turns out that there are two choices that will make sense. So once again, we're kind of into the land of making the clever versus the unclever choice. So we'll start by going with what would be the unclever choice here. Not that in this case the algebra is all that much worse if you make the unclever choice versus the clever one, but bear with me. And we'll pick our axis of rotation to be here. Now you might think that that's the only choice you could have, right? Because after all, that's where the fulcrum is. But consider that in this case here, our plank is not rotating. If it's not rotating, not only is it not rotating about this axis that I just drew, it's also not rotating about any other axis that I might want to draw. And so we'll first go ahead and do it with this choice, and then we'll go ahead and do it with a different choice, just to show that the algebra can be at least a little bit easier. So we'll go ahead. This is the L1 we want to know. And then we already worked out that this was L minus L1. Well, we called that L2. All right. So when we go ahead and write down the sum of the torques being 0 here, what we have, we're going to have, first we'll look at the counterclockwise torques. We'll have the only force that's trying to twist our teeter-totter counterclockwise is the force of gravity acting on the heavy kid. So that will be Fg1 times the heavy kid's lever arm L1. Then we look and see, are there any forces trying to twist it clockwise about this axis? And the answer is the only one is Fg2, trying to twist it clockwise. Clockwise torques are negative, so this will be minus Fg2 L2 equals 0. Now you might wonder for a moment, hey, but what about the normal force? Yeah, but remember, the normal force is going actually at the axis of rotation, so it's a slam dunk that the line of action goes through the axis of rotation, meaning the lever arm for the normal force is 0 here. So if you didn't have to solve for the normal force, this is probably a good choice here, because then we could have skipped this whole balancing the forces in y, because we wouldn't have needed to solve for the normal force at all, since the torque due to it is 0. But since we're asked to solve for it, we'll see that there's a faster way to get the lever arm in a moment. But let's just do it this way for the moment. So we will substitute in everything. This is M1G L1 minus M2G, and we said that L2 was L minus L1. That equals 0. Now, I can divide both sides through by 0, and I will just get that the g's cancel out, right? 0 divided by g is still 0. And so we're left with, so once the g's cancel out, we get an interesting bit of physics from that. We realize that literally everywhere in the universe, the game of teeter-totter is played exactly the same way. All that matters is that there is a gravitational field. It doesn't matter how strong it is. The way you balance a teeter-totter is the same literally everywhere. All right, well, anyway, let's go ahead and start solving for L1. So let's see, So M1 L1 minus M2 L2, minus is a plus, M2 L1 equals 0. All right, so we're going to get that, sorry, that's just L, not L2. There we go. So we're going to get that L1 is equal to M2L over M1 plus M2. Okay, so we can put that in. That is going to be 25 kilograms times 3 meters over 25 kilograms plus 50 kilograms. That'll give us 1 meter. All right, and that's basically exactly what you expected from having played teeter-totter as a kid, I'm sure. All right, but let's just repeat this analysis for a moment. And we'll do it again, but with the more clever choice of free body, rotation axis. So once again, our system is the plank, and we got ourselves the heavy kid. We got the skinny kid. There we go. Oops. That leg's a little weird. There we go. That works. So we'll go ahead and draw in our forces just like before. So Fg1, Fg2, normal force. All right, and just real quick, we'll repeat the analysis that sum of fx equals 0 is boring. Sum of fy equals 0. We have n minus fg1 minus fg2 equals 0. So normal force is fg1 plus fg2 is m1g plus m2g is m1 plus m2g is, 50 kilograms plus 25 kilograms times 9, oops, it's a 9.8 newtons per kilogram. And that gives us the 735 newtons we had before. All right. Now, let's go ahead and remember what our goal is. The question asked, how far from the heavy kid should the teacher put the fulcrum in order to make the game fair? So we're asking for L1. Now, what's given already is the distance of the length of the board. We were given that was 3 meters. And so the trick here is that we decide to put our axis of rotation right here. Remember, the whole thing is that if the game is fair, we're not rotating. The kids are just sitting there. So we are not only not rotating about the fulcrum, but we're also not rotating about the heavy kid. Now this has the advantage that we can just put in our L1 and our L, and the algebra will be a little cleaner when we balance the torques. Let's see how this goes. So we'll have sum of torques, oops. There we go, I'll just do that. So sum of torques equals 0. So now what's trying to twist our board counterclockwise? Well, about this axis, it's the normal force. And the lever arm for the normal force is L1. What's trying to twist it clockwise? FG2. But now the lever arm is the whole length of the board, L. Now the force of gravity from the heavy kid, that isn't trying to twist it about this point at all, for the exact same reason. The line of action is going through the axis of rotation, so the lever arm is 0. All right. So let's just go ahead and put everything in. So from before, when we solved, we got the normal force was m1 plus m2g, L1, minus the force of gravity on object 2 is just m2g, L, equals 0. And once again, the game of teeter-totter is played the same on every planet in the universe. And we can solve for L1 and get that it is m2 times L. Oops. Try that again. m2 times L over m1 plus m2, which is the exact same result that we got before. So we'll just stick in the numbers for the funsies. So you get the same answer either way, but you can see the algebra is just that little bit easier. You didn't have to distribute across this L minus L1 kind of thing. And this is just something to keep in the back of your mind. If you run into a problem where they say, where should I put the pivot? It's often faster, even if you aren't asked to solve for the normal force. Here it's a wash. But say if we were to have 2 more kids on the teeter-totter, let's say, it will actually be faster to solve for the normal force from the fulcrum, even if you weren't asked for it in the problem, and to then set the axis of non-rotation, as I like to call it, at the point you're measuring from, just to get rid of all of these kind of L minus L1 things that show up. Makes the algebra a lot less complicated. At the end of the day, it doesn't really matter which way you do it. Either way you do it is fine, and you'll get the same answer either way. But just something to keep in the back of your mind. This is a little quicker. All right. Well, let's go and do a slightly more complicated problem. Let's say that we happen to have a perfectly good exterior wall to which we are going to attach a sign for a business. We'll hang the sign out on a 4-meter long pole, or we'll hang it so the center of the sign is 4 meters out. We'll put it that way. So here's the center of the sign. And we'll say that this distance right here is 4 meters. We will attach a guy wire 3 meters up that attaches directly over the center of the sign. So we'll say that distance is 3 meters. And I do this just so I can make this angle here 37 degrees. Okay, 36.9, but we'll call it 37 degrees. Remember, 37 and 53 degrees are the interior angles of a 3, 4, 5 right triangle. All right. So, and then right here, we're going to have a hinge. And so the hinge will be exerting a normal force. Now, what I'm going to want to get out of this is the magnet is how much is the tension in the cable, and what is the magnitude and direction of this normal force. So at first you might look at it and say, well, gee, it's got to be perpendicular to the wall, duh. And it actually turns out that's correct in this case, but let's say we didn't know that. You would just in general put the normal force off in some direction, and we don't know what this angle is. And we would be dimensioning out an x and a y component for the normal force. And before you think that seems a little crazy, if you look at the construction of a hinge, what you've got is a pin that's sitting inside a sleeve. And so when the hinge is, hinging, the pin is free to sit wherever it needs to on the inside of the sleeve. And so it can exert a normal force, say, in that direction if the pin's like that. If we're down here, it would be exerting a normal force down, and so forth. So there's always a little bit of slop, and the point of contact between the pin and the sleeve dictates where the normal force is pointing. All right, so let's just go ahead. We don't quite have enough information yet. We need to know that our sign has a mass of 10 kilograms. And because I'm not trying to kill anybody here, we're going to make the cable massless and our bar massless. Okay, so let's go ahead and we'll just draw since I've already drawn in the normal force, let's just continue drawing in our extended free body diagram here. So the force due to tension acting, so our system here is going to be the beam, our massless beam here. The force due to tension will be acting here at this connection point 4 meters away from the hinge. And the force of gravity will be acting at the center of mass of the sign. Again, 4 meters from the hinge, but at some distance below that will turn out not to be relevant. All right. So here we do want to know both the tension and the normal force. Now, because we've got two unknown components here, the normal force in x and y. In this case here, following the same sort of game we were playing with the teeter-totter, it will be most convenient to put our axis of rotation, or more properly, I guess, an axis of non-rotation at the hinge. Again, we're free to put it anywhere. We could stick it over there if we wanted to. It just wouldn't be that helpful. But we'll stick it here, and I'm purely doing this because although the forces won't be zero, by putting the axis here, the torques due to the normal force will be zero, and that will make the problem easier to analyze. All right, so let's go ahead and at least do the forces. So sum of Fx equals 0. That's going to give me, well, we've got the x component, the normal force pointing to the right. And then we've got the x component of tension pointing to the left. So that'll be t, we'll call this angle theta here. T cosine theta equals 0. All right. And we can do the same game with the sum of the forces in y equals 0. So again, here, we'll have an upward component to our normal force, so we'll have an ny. We'll have t sine theta pointing up, and then the entire force of gravity of the sine pointing down. All right. Now what's left is going to be to find the sum of the torques about our axis, and we know that those have to be 0 as well. So now we need to define our lever arms. So we'll go ahead and identify the line of action here. So the line of action for gravity is this. Okay. And so this distance, if we call this 4 meters here, r, that is our lever arm for gravity, so I'll call it r perpendicular g, and that is 4 meters. Okay, great. So, sum of torques equals 0. So that's going to give us a clockwise torque there. Now for our counterclockwise torque, I'm going to do it the other way. Instead of finding the lever arm, I'm going to use the tangential component of the force. So this bit right here is the tangential component of tension, which will be equal to t sine theta. So what I can go ahead and do now is say, all right, tension is trying to twist the whole system counterclockwise around the axis. So that is going to be r times the tangential component of tension, because I'm choosing to write that one that way. And then here for gravity, I'm going to say it's the lever arm times the force of gravity. So that'll be minus, because it's clockwise, r perpendicular gravity times Fg equals 0. All right. Well, anyway, we found that the tangential component of tension is t sine theta. In this case here, r perp for gravity is just this distance r here. So we can just write this as r, and the force of gravity is mg equals 0. Interesting, and maybe a bit unexpected. It turns out that the tension is only going to depend on the force of gravity here. And actually that's not unexpected, but I'll leave that for you to think about that. Anyway, we get that our tension force will be mg over sine theta, which makes sense because the more oblique this angle, the bigger tension is going to have to be, because a lot of it's directed sideways. So the more oblique this angle, the more sideways I'll have to get the same amount of vertical. All right, 10 kilograms times 9.8 newtons per kilogram over the sine of 37 degrees. We get that our tension is 163 newtons. Yay. So we got that. So now, pretty much immediately, we can go ahead and get the x and the y components here. So first, let's look at the y component for the normal force. So the sum of Fy equals 0 gave us ny plus t sine theta minus, well, the force of gravity is mg equals 0. But if I add mg to both sides, what I get from here is that t sine theta equals mg. So I can note that that's mg. And since those are both equal to mg, that means that they cancel each other out. And we get that the y component of tension is 0. And to a certain extent, it should be a bit unsurprising, because if you go and look at the axis, with the axis over here, what we have is that the y component tension had to exert what was responsible for exerting the counterclockwise torque to balance the clockwise torque from gravity. And since they both had the same lever arm, they meant that the two forces would have to be the same. So that's why I was saying that if you stared at it for a bit, because these were in a line here, we knew that the y component of the normal force had to be 0. But if you didn't know that, that's okay. You set it up and you solve for it. All right. Now let's pick back up with sum of fx equals 0. So now this was nx minus t cosine theta equals 0. So now what we found is that our normal force is directed entirely along x, because we discovered that the y component is 0. We also know that it's pointing to the right, because the only other force we have is acting to the left. Oops. So our normal force is t cosine theta. So this is 163 newtons times the cosine of 37 degrees is 130 newtons. And it's directed to the right in order to balance out the leftward tug from the sine. Alrighty. In the next video, we will go ahead and start to, we'll take a brief detour to look at the condition of rolling without slipping and see what that means. Catch you over in the next video.